Hello Year 10s and welcome back to Mathematics. In today's lesson we're continuing with our topic of properties of geometric figures and we're talking about similar triangles. So in the last lesson we talked about congruent triangles, triangles which have the same shape and the same size. Today we're going to be looking at what similar triangles look like. So for today's learning intention and success criteria, we want to be able to understand and apply similarity in triangles, and we want to be able to identify the tests for similarity in triangles, prove that two triangles are similar, and then use similarity to find missing sides. So let's get started. Firstly, let's give just a quick definition of what similarity is. So, two triangles are similar if they have the same shape, so just like congruent triangles, and you have the exact same shape, but not necessarily the same size. This is where a triangle may be an enlargement of another. What will happen here is that the matching angles will be the same size, and matching side lengths will be in the same ratio. So what this looks like is if we have a triangle and if we have two triangles, they're similar if they have the exact same shape, but they might not be the same size. And so what this means is that one of them is maybe just be a bigger version or a smaller version of the first one. So for example, if I have this example here, I've got this triangle ABC. And if I select this triangle and I copy it, the way that we can create a similar triangle is if I get this exact same triangle. So if this exact same triangle is congruent, but if I enlarge it like that, this is now a similar triangle. It has the exact same shape. And the way that we know this, and I'm actually going to label this triangle as DEF, it has the exact same shape. The reason we know this is because all of these angles are exactly the same. So here, this angle is going to have this exact same size as this angle over here. This angle at B is going to have the exact same size as this angle at E. And this angle at F is going to have the exact same size as this angle at C. So even though we enlarged it or shrunk it, the angle sizes will still stay the same. So that's what it means for it to have the exact same shape. Now, the other bit is that the sides are in a matching ratio. So for example, here, notice in the first one, I've actually labeled the sides 1, 2, and 3. So we're just pretending that these have side lengths 1, 2, and 3. In order for them to have matching side lengths in the same ratio, what this means is if I had one of my side lengths, so for example the one with 1, so BC was 1, the matching side on my similar triangle, second triangle is EF, and let's say the matching side on EF was 3. So what this means is that in order to get from my first triangle to my second triangle, I need to multiply by 3. So I need to multiply all the side lengths by 3. And so for it to have matching side lengths to have the same ratio, what it means is that this number needs to be consistent for all 3 of my sides. So for example, AB had a length of 2. And so for DE, if we need to keep this ratio the same, that means I need to multiply that 2 by 3 so I can get a side length of 6. And for my last side, AC in my first triangle was 3. And so in order for me to keep this matching ratio, keep them in the same ratio and consistent, I need to just multiply that by 3. And so this last side, it has to be 9. And so here, this is what it means. Same shape, but not necessarily the same size. But for all of the matching sides, they need to be in the same ratio. So I need to make sure that there's a consistent enlargement factor happening for all 3 of my sides. So that's what it means for two triangles to be similar. Same shape, not necessarily the same size. So just like we had for congruence, there's actually a bit of notation that we use for similarity. And I'll move this up just so you can see. So here we've got my two triangles, ABC and DEF. If we want to write down that two triangles are similar, the symbol that we use is 3 vertical lines. So if you remember, when we wanted to say that, so this is a symbol. So this is a symbol for similar to. So if you remember from when we did congruence, the symbol for congruence is 3 horizontal lines. For it to be similar, it's just 3 vertical lines instead. So this is what it means for a triangle to be similar, and also how we write similarity for two triangles. Similar to, just like we did for congruence, we also need to make sure that the corners of the triangle match up. So here, A matches up with D, so A matches up with D, so the first letter happens to be A and D. So here, A matched up with, let me try that again. A matches up with D, B matches up with E, and C had to correspond to F. And so just like we did with congruence, we just had to make sure that the corresponding corners match up in our two triangles when we write them down. Now, just like we did with congruence, there's actually 4 tests, just like congruence, for us to check whether or not two triangles are similar. And so these are ways that we can see these. If any of the if two pairs of triangles, if they pass any one of these 3 tests, that means that they are similar. So let's go through the 3 tests. So the first one, 2 angles of a triangle are equal to another. So if you get given 2 angles in a triangle, so for example this one here and this one, and they match and they're equal, and this one over here and this one over here, then they're equal, that is a test that allows me to check whether or not 2 triangles are similar. So if you've got 2 pairs of equal angles, that means your 2 triangles are similar. The second test is that 3 sides of a triangle are proportional to the 3 sides of another triangle. So what this means is that this just means that to get from one triangle to the other triangle, there's that consistent multiplication or that consistent ratio that's being kept. So for example, like in the one that we had up above, so let's say I had my 3 sides. So let's say this one was called A, this one was called B, and this one was called C. Ooh, let me try that one again. Let me rewrite that. In order for it to, for any triangle to fulfill this test, all it just means is that we have to keep that consistent ratio. So if I go to the second one, I could be any number. Let's say I actually had to multiply by a number, let's call it K, to get to the second triangle. So what this means is that this side over here, in order for it to be consistent and proportional to the other one, it needs to be K times A. Let me write that in yellow actually. K times A. For the green side, it had to be K times B long. And this one has to be, this last one has to be K times C long. So here, if the 3 sides of the triangle are proportional to the 3 sides of another, so it keeps that consistent ratio, that means that is also similar. The third test is if 2 sides of an triangle are proportional to 2 sides of another triangle and the included angle are equal. Now this is similar, so it's similar but not quite equal to the SAS test that we had in congruence. So what this looks like is if I've got one side of my triangle, so this one A, and it's proportional to the other, this matching side in my second triangle, so for example K times A, I have another side, so let's say B, and this second side had a length of K times B, and the angle that's inside here, if these 2 angles are equal, that means that my 2 triangles are similar. So this is similar to that side angle side test. Notice we've got 2 sides. So the pink side, they are in the same proportion. The green side are in the same proportion, and the angle that's between them is equal. If that criteria is fulfilled, that also means that my 2 triangles are similar. Now the last one is similar to our RHS test. So if you remember our RHS, similar to RHS, it's right angle, hypotenuse, and another side. So here, the hypotenuse and the second side of a right angle triangle are proportional to the hypotenuse and the second side of another right angle triangle. So in order for a pair of triangles to pass this test, is if they have, firstly, a right angle. So both triangles need to be right angle triangles. And then they need to have the hypotenuse, let me write this in blue, the hypotenuse needs to be in equal proportion. So just like we did before, so if this one is C, this longer hypotenuse also needs to be K times C. And then any side, so any third side, so here for example if it was B, then this side over here needs to match up with K times B. That K number being how much bigger one triangle is compared to another. So these are the 4 tests that we need to use when we're trying to test for similarity. Now, the first thing that we actually want to do is we want to be able to prove similarity. Now, proving similarity, this is very similar to the steps of proving congruence. So when we want to prove similarity, it's going to be fairly similar steps to proving congruence. So here, the first step that we do is we identify the similarity test that we're going to use. So here, it's going to be one of these 4 tests. So we want to identify which of my 4 tests am I going to use in order to prove that my 2 triangles are similar. And so you want to just look at what information you get given about your 2 triangles. Then from there, you want to state each piece of evidence from the diagrams that form the similarity test. So you just want to write, if 2 angles are equal, you just want to write that this angle is equal to this angle. And then for the final step, we just want to write a concluding statement. So just a similarity statement for our 2 triangles. So let's have a go at a couple examples just to get an idea of what this looks like. So let's have a look at this first one. Prove the following triangles are similar. A, we've got these 2 triangles here. Now, if you have a look at the 2 triangles, what information are we given? Well, in both of the triangles, we have this angle over here, 70. We have this angle over here, 70, that matches up. And we've also got this angle 30 and this other angle 30 that match up as well. So if you have a look at my 4 tests, this is just the same as the first test. We have 2 angles of our triangle and they're both equal to one another. So what I'm going to say, this is going to be using test number 1. I'm just going to call it test 1 just to make it easier for myself. Now, when I'm proving that they're similar, all I need to do is just write down each piece of information that I have. So let's first start off. Well, I've got 30. This angle of 30 degrees is equal to this angle of 30 degrees. So I'm going to write here angle ABC in my first triangle. That is equal to angle DEF in the second triangle. So that's my angle. Okay. The second one was that I've got also this other angle of 70. That's an angle BAC. So just remember with angles, the middle letter is where the angle is. So the middle letter is where the angle is. And so that's equal to, in my second triangle, that is equal to, so 70 is equal to EDF. And so because of that, now that we've got that information, we've got 2 angles. Using our first test, we've passed the first test. So therefore, that means that our 2 triangles, triangle ABC, is similar to triangle DEF, and we just want to make sure that we write it in that matching order for the corners. So that's quite simple. So if we get 2 pairs of matching angles, that's enough for it to test for our 2 triangles to be similar. Okay, let's have a look at this next example. Now here, what are we given? Well, we get given all the side lengths of my first triangle, and I also get given all the side lengths of my second triangle. Now, if you have a look at those numbers, what do you notice? Well, actually, these numbers actually match up. So for example, if I have this 7, well, what number on the right hand side looks like it matches up with 7? Well, 14. 14 is just 2 times of 7. And if I look at this 5 over here, well, what number matches up with 5? Well, there's this 10 over here, which is just 2 lots of 5. And so in order for me to get from my first triangle, I need to multiply by 2 to get to the second triangle. So for the side lengths at least. And so we can actually check that with the last one. Well, 8 times 2, that gives me 16. And so here we've got 3 pairs of matching sides which are in the same proportion. If you have a look at my 4 tests, this is test number 2. 3 sides of a triangle are proportional to 3 sides of another triangle. So here, the value of k is 2. In order for me to get from one triangle to the other triangle, I actually multiplied all the side lengths by 2. And so here, I'm going to be using test 2 for this one. And so for this one, this is a little bit different to all the other proofs that we've actually written. What I'm actually going to do is I'm actually going to write down each pair of matching sides as a fraction. So for example, in my bigger triangle, I had the side DE. DE, I'm going to divide that by the matching side in my first triangle. So DE matched up with AB because that's equal to 10 over 5. 10 over 5 is just equal to, 10 divided by 5 is equal to 2. And I'm going to repeat this process for each pair of matching sides. So the next one would be, let's do DF. And in my smaller triangle, that matched up with AC. And so that was 14 over 7, which also equals 2. So here we're seeing that we've got this consistent number that we're multiplying to get from the bigger one, from smaller one to the bigger one. And the final one was BC. And if you have a look, BC matched, other way around actually. EF matches up with BC, and so that is 16 over 8, which also gives me 2. And so here we've got that consistent ratio that we need to multiply each term by. And so here, because of that, and test 2, therefore, triangle ABC is similar to triangle DEF, because each pair of sides are in that equal proportion. And so here, if we want to show equal proportion, we need to do one of these statements. We divide the two pairs of matching sides, and then we want to just show that number is consistent each time. The other thing is we want to also just make sure that we have the bigger triangle at the top. That just makes it more consistent, and the smaller triangle at the bottom, and that makes it a little bit easier for us. Okay, let's have a go look at the next one. Next one here. Now we've got my two triangles A, B, C and D, E, F again, and we just want to see what pieces of information we have in this diagram. So here we've got two sides in my first triangle and an angle in between. And in my second triangle, I've got also two sides and the angle in between. And so if we look at our four tests, this one looks a little bit like test number 3. Two sides of a triangle are proportional to two sides of another triangle, and the included angle are equal. So here, if you have a look, I've got my two sides and I've got the angle between it. So I'm probably going to be using test 3. Now here, what we want to do is lay out all our information. So let's start off with the angle, because that one's the easiest one to do. So here, angle BAC in my first triangle is equal to angle EDF. So they're both 80 degrees. And then the next part is I want to just show that each one of my sides are proportional. So here I want to find what matching sides I have, and then just write it as a fraction and just show that the value that we get from that fraction is consistent for all the way through. So here, if I start off with this one, AB, well, that matches up with, well, A is the angle, and we want to look for this next side. So that kind of matches up with DE. So here, what I'm going to write is DE over AB. Now let's put that in. So DE was 3 over 2 for AB. So 3 over 2, if I put that in my calculator, just becomes, I believe it's 1 over 2. 1.5. 1.5. And so here, this is 1.5. Okay, let's do the same thing for my other two. So my other two matching sides is AC and DE. So I'm going to write here DF over AC is equal to 4.5 over 3. Now let's put that in a calculator. So 4.5 over 3 also gives me 1.5. And so here we've got that consistent number which we're multiplying to get from my smaller triangle to my bigger triangle. So by doing that, we've passed test 3, and so that means that my two triangles are similar. So I'm going to write triangle ABC is similar to triangle DEF. So that's how we can prove similarity using our third test. Let's have a look at the final one. Now here, if you have a look, there's an immediate clue that tells you need to use test 4. The immediate clue here for me is this right angle over here. So that usually tells you need to use the RHS, or we've got a right angle and a hypotenuse and another side in equal proportion. So that's test number 4. Now let's lay out the important pieces of information here. Now with this one, because it is a right angle, we need to also specify that the right angle is 90 degrees. So for example here, angle in my first one, it's angle BAC, and that's equal to angle EDF, and they are both equal to 90 degrees. In order for us to actually pass this last test, we need to have it being a right angle triangle. And so we need to specify that that angle is indeed 90 degrees. So here I've written that it's 90 degrees. Then what we're going to do is just check for each pair of matching sides. So here, AB matches up with DE. And so we're going to do that ratio comparison. So I'm going to write as a fraction, DE over AB is equal to 7.5 over 5. Let's find out what 7.5 over 5 is. So 7.5 over 5. That gives me 1.5. It happens to be 1.5 again. So here I've got 1.5. Then the next one is this side here. So BC and EF, they match up. So I'm going to write BC over EF. And so I'm going to have, it's actually the other way around. I want the bigger triangle, don't I? Yep. So it's going to be EF over BC. And that's 16.5 over 11. Let's just put this in the calculator. And if it's equal to 1.5, that means I've got similar triangles. So 16.5 over 11. That gives me 1.5. Yeah, excellent. So here, this 1.5, because it's consistent for all of my matching sides, it means that we've got a pair of similar triangles. So here, therefore, once again, triangle ABC, I'm just writing this statement at the end, is similar to triangle DEF. So there we go. That's how we can prove similarity. So just like we did with congruence, we want to lay down all pieces of information. The only thing that is different here is when we're dealing with sides of our triangle, we need to actually write that as a fraction and divide the two terms together. So, and check that all of the sides are in the same ratio. So each pair of sides have that same number that we're multiplying by to get to the biggest triangle. Okay, so that's proving similarity. Now, the final thing that we want to do is actually find missing sides using similar triangles. And so here, this involves something called a scale factor. So a scale factor is the number required to multiply the side lengths of a triangle to enlarge or reduce its side. And this is found by dividing the corresponding side. So we've actually dealt with this scale factor before, but we haven't actually called it that. So all of these numbers that we have here, so this 1.5, 1.5, 1.5, 1.5, 1.5, 1.5, all this is 2. This is a scale factor. It tells me what do I need to multiply my smaller triangle by and all the side lengths by in order to get to the bigger triangle. And so here, there's actually a scale factor formula. The way that we do this is we take the, the image length or the enlarged version. We call this the image length. So how long is one of the sides in our larger triangle? And we divide it by the original length. So the corresponding side in the smaller triangle, how long is it in the smaller triangle? And so we've actually done this for all the examples above when we were proving, we just never called it that, and now we're actually going to apply it to help us find missing sides. So when we're trying to use this scale factor formula, what we want to do is identify two corresponding sides in the triangles, then divide the two sides, and this number is the scale factor. And just like we did before, usually you put the largest measurement at the top and the smaller measurement at the bottom. Then, if we want to apply this and actually find missing sides, what we do is we multiply or divide a corresponding side to find the version in the bigger or the smaller one. Now here, multiply or divide. Now this is where if you're not sure, you actually need to check what triangle you have. So if you have the measurement in the bigger triangle, you're going to divide. So this is if you're going from the bigger triangle to the smaller one. But if you're going from the smaller one to the bigger one, you usually want to multiply. So this is if you're at the small and you want to go to the bigger triangle. So the operation that you use here depends on what type of question you get asked. Are you trying to find the missing side in the smaller triangle, or are you trying to find the missing side in your bigger triangle? So let's go through an example of this. Example 2. The following two triangles are known to be similar. Find the value of x. So here they tell us that these two triangles are similar, and the way that we can tell this is if you have a look at the diagram, we've got two pairs of equal sides here, and we've got equal angles over here, and two pairs of equal angles over here. And so this actually passes the first test, test 1. And so if you have a look at the diagram as well, what we've got in our first triangle, we've got this side is here is 2, and this side here is 3. And in my bigger triangle, this side over here is 4, and this side over here is x. So we want to find this value of x. And so the way we do this is we need to first find the scale factor. We want to find two corresponding sides which we have the measurements for and find that scale factor. So if you have a look here, well, I've got this side 2 over here. That matches up with this side 4 over here. So if you have a look, they're in the same spot. They have the two angles, the red angle and the blue angles at either end. And so these two sides are going to be corresponding. So here I'm going to use my scale factor formula. And so I'm going to have, the scale factor is 4 divided by 2, which just gives me 2. So what this tells me is if I want to find the measurement in the bigger triangle, I'm going to be multiplying by 2. So if I want to find x, all I need to do is find the side that corresponds to x in the smaller triangle and multiply by 2. So if you have a look, the smaller side that corresponds to x in the side that corresponds to x in the smaller triangle is 3. So all I need to do is just do 3 times 2, and so it gives me 6. And so that tells me that x has a side length of 6. So that's it. That's how we can apply this scale factor formula to find missing sides. So that's it for today's lesson, Year 10. So let's just do a quick recap of what we talked about today. In today's lesson, we talked about similarity. And so similar triangles have the same shape, but not necessarily the same size. So all the angles in my triangle have the same, in both the triangles are the same, but the side lengths might not. And so what we want to do here is we want to just check that they have are being multiplied over by the same consistent number, so the same ratio. We went through testing similarity. And so we went through testing and also proving similarity. So we went through the 4 tests that we use to test for whether or not 2 triangles are similar. We went through how to prove that triangles are similar. And the final thing was we actually found the scale factor and used that scale factor to help me find missing sides in my triangle. So that's it for today's lesson, Year 10s. If you have any questions, feel free to ask me or send me an email. I'm more than happy to try and answer your questions. And until then, I hope you guys are staying safe wherever you are, and I'll see you in the next lesson. Bye.